So let's begin. So on my screen and the voice working now. So if no problem, I can continue. Okay. So this talk is about our recent work about in-factor learning. So the first part is about the security framework for factor learning. We have three published works. And the second one is we want to combine the blockchain in factor learning, and we use the blockchain to replace the aggregator in factor learning. And the third one, we do some wireless optimization, such like the client scheduling and the channel optimization with wireless factor learning. So let's begin. So in chapter one, we introduce the background in factor learning, as we know that the data is growing with the number of intelligent devices and applications. So how to process the data is now a kind of hard problems. A traditional machine learning way to use data to do the machine learning tasks is like we need to transfer the data to a central server and use the central server as a center to do the machine learning task. But it has some drawbacks. For example, the transmission burden, because we need to transfer a huge or a large number of data like the figures, videos, or table data to the center. And we have some information linkage during the transmission. So the factor learning is proposed in that way. As we know that in factor learning, and we talk is about horizontal factor learning, and we will mention some vertical factor learning in the future works. The procedures that the clients don't need to transfer the data to the center server, and they only need to compute learning models with their own data set and transfer the learning models, or like the learning parameters or gradients to the aggregator. And the aggregator can do the model aggregations and send back to aggregate the models. So this is a typical process for the factor learning. And we introduce some advantage for factor learning. So because only the models are transferred between the clients and the server, so they can reduce the transmission bytes. So we can achieve a high efficiency for the communications. And also it can mitigate the risk of information linkage, because not the real data can be posted to the adversaries or image droppers, because the data is changed to like the model parameters or something like that. So it's not that easy to analysis the data or the import the data. So let's to the main part. In the first chapter 2, we do something about the security or the differential privacy in factor learning. We began to study or conduct the factor learning in 2019, and we began to write a magazine paper about the security and the privacy in factor learning in IEEE network. And in that paper, we show some potential risks in security and privacy, and propose some solutions. So the first one is you use differential privacy in factor learning. So here is a system model. In this system model, we consider that in a horizontal factor learning system, the clients will upload their learning models to a reliable server. But during the transformation, there may be some external adversaries or eavesdroppers. They can hear the transmit models. And we know that there have existing technologies like the GN, general adversary networks. They can transform the learning models to real data, or they can generate real like the data very similar to the training data set. So in this way, the privacy can be linked. So we apply the differential privacy into the transformed transmitted models. So we will introduce the differential privacy first. It have a formal equation in the red color like this. It defines the two probabilities and the optional the parameter optional define the privacy level. For example, the optional is close to one. If the optional is larger, we mean that the privacy level is low, and the optional the option equal to 0 is close to 0, we can see that the privacy level is high. So the idea is quite simple, that when the clients, they upload the parameters or learning models to the server, they will add a random noise, for example, a Gaussian noise, or not random noise from the Gaussian distribution to the learned models, and the aggregator or the server will aggregate announced parameters and do the rest of the training. So the idea is same that if you do something about the differential privacy in deep learning, you have read a paper in 2016 in CCS. They gave a clear and clear explanation about how to use DP in deep learning. So the idea is same. And in this work, the main contribution is that we are the first to do the convergence analysis in differential privacy for federated learning. And we have some assumptions. The the first assumption is that the loss function for the machine learning model is convex. And for our appearance, we know that the convex option is quite strong. So in the later or in this year, in our recent published works, we usually assume that the loss function is non-convex. But in that paper, because it is right in 2020, so it's quite old one. So we just can assume that the loss function is convex, and we can give a convergence upper bound for the learning performance. And from this bound, we can give some iteration. For example, the aggregation time t, and n, it denotes the number of clients, and the optional denotes the privacy level. So there are some remarks. For example, if we increasing optional, which means the we decrease the privacy level, so the performance will improve, and a large number of clients will lead to a higher performance. And also because we add noise to the parameters, there exists an optimal number of aggregation time t exist in the whole convergence performance. So this is the first algorithm, and then we use another one that we don't choose every client in each communication round. When we use we randomly choose k clients, and the conclusions or the results are quite similar, but it's more complicated. So we come to the experiment result. We use the miniest dataset for the result, and we use multi-layer perception for the machine learning model, and we set the learning rate to this value. And first, we can find that the theoretical results are quite consistent with the simulation result, and they are also exceed the optimum point. For example, the optimum point here denotes that there is optimal aggregation times in the total training process. And then we do other results to verify the remarks. For example, this one, we increase the knot powers, which means that the optional, we decrease the optional, and we can find a large optional from the yellow one can can bring about smaller loss function values. And we also the sorry, the aggregation number of the number of aggregation time is like the communication round. Like for example, the client will do sometimes of the local epoch trainings, and then they will send models to the aggregator, and this process called one aggregation time. Then the aggregator will collect all the received parameters. Is you mean you mean the aggregation time here T is like the communication round, and the loss function is the global log. This is the global loss function. Yeah, right. So can we continue? Okay. And we also do some result for the random scheduling, and it also verify the remarks. And I didn't spend that time on this slides. So we come to the next work. We publish in IoT journal. We conduct something about unreliable clients. This is the system model that the client they may behavior unavailable because intentional like the malicious client, or unintentional because the hardware or software has limitations. So we gave the parameters or the learning models they transform to the aggregator. It's not that perfect, and we gave like the unreliable models like in this way. It have two parts. The first one, alpha. So for first, the omega I is the original learning models, and the alpha indicating a scaling factor, and the n denotes the random noise. So the unreliable client, the parameter of the unreliable clients can be defined that this way to have two parts. The first one is like the way intentional, malicious client intentional dictating the learned parameters. And the second one is that some random nodes are unintentional inject into these models. And we also we have the probability to define the reliable behaviors, and this probability is predefined. So we use this equation to do some system performance analysis, and we can also get some observations. For example, we can find that with decreasing the unreliable probabilities or when increasing alpha, we can improve the performance. And also we can improve the performance when we have a large number of clients participating in this learning. And we also know that the learning performance is a convex function with the local epoch tau. Here, the tau means that in each communication round, uh, each client will do like the tau times of the local trainings, and then transmit the learned models to aggregator. Okay. So this is the model that we use to define the unreliable clients, and then we design a defensive mechanisms called a deep SA. It has offline training procedure, unlike the other robust aggregation rules we will define later. So they have two parts. The first one is the fully collected hidden layers, and the second one is like the conventional layers. And we can combine these two networks to define the two unreliable behavior. For example, the unreliable and the unintentional and intentional behaviors. So this is a algorithm that we define deep SA, and we show the result first. So some experiment results about the unreliable probabilities we can find. So if PU equal to 0, so we can say that the whole environment is trust, and we can see the decreasing the number of occurrences is decreasing with the number of local iterations. It means that we in the true factor learning, we need to set the local epochs equal to 1, and this can get the best performance. And if they are except or they have some unreliable clients, we can say this a convex curve, and they're all exceed the optimal number of local iterations for the fashion mix and C510 mini data set. And then we compare the deep SA with other 3 robust aggregation rules. First one is the Chrome, and the second one is Pearson, and the third one is security probe. And we use 3 cases to define the unreliable clients. For example, the first one, the alpha equal to -1. It means that the whole learned parameter will complete inversed. And the second one, we will inject a large value of random noise. So we compare the performance with in full data set, means the fashion means C510 or adult data set. We can find that the proposed deep SA, because it has the best performance. The main reason is that because it have offline training procedures, so it can well capture the bad behaviors. So we come to the third work. The third work is a quite interesting one. In this work, we want to design attacking method in factor learning, and we use a mode positioning way to define the attacking method, and it submit to the TDSA because we try the SP because if anyone kind of familiar way, we tried the SP, but we didn't get a positive result, so we submit to the TDSA. So the attacker have 2 aims. The first one is anti-targeted attack. Its main result is to degrade the learning performance. And the targeted result is that it will mislead the trained model to a designed result or desired direction. And we will show some results in these 2 aims later. There is an assumption in this result because because we want to optimize the attacking method. So so for example, this one is a malicious client. He has to know the aggregation rules in this factor learning system, and he can use these rules to define the attacking aim, and he can use this equation. Here we define optimization from for the attacker because this is attacker to degrade or to target attacking one goal. And this is algorithm. I didn't go to the very details because it will waste a lot of time. I just show the results. So for the untargeted results, we show in the minutes data set, and we can see there are total 50 number of clients, and there are 10 malicious clients, and they are the group. The malicious clients are a group. They have the same goal. So we can compare with other 2 attacking methods. We can see that the proposed untargeted result has the highest error rate and the highest attacking rate. But because it composed of the optimization process, so will cost a lot of time. And we also show the target attacking results. For example, the original dictal in this dataset is 9, and we want to train that to train the aggregator that he can recognize 9 to 0. So after around 200 iterations, we let aggregator to mislead the model to clarify the data 8 to 0. It's like we give the aggregator a predefined directions, and the aggregator will use this direction to optimize his classifier, and it's like the target attacking result. And also, so that, for example, the 1 to 2, the 1 to 2 after 200 iterations. And also try in the fashion to the CIFAR minutes, CIFAR 10 data set, but the result is not that good. But in the predict result, we can see the original image is a house, and sorry, the original image is a house, and the predict result is a frog. But we all know that it's the house, so it's also working in the fashion CIFAR 10 data set. Okay, so the first part, because maybe I'm a little little fast. The first part is in. So that have anyone have other questions? Maybe I can try to answer your question before I explain the rest two part. Or maybe we can move this part to the Q&A and A question section. Okay. So in chapter 3, we introduce the blockchain to, okay. The non-ID pyramids is but we have some code because we want to define the non-ID non-ID behaviors or the settings, but we try to Google the papers. We didn't have a formal settings or formal declaration for the non-ID. So commonly, formally we use that. For example, some clients they don't have all the labels for one data set. For example, in the minutes data set, maybe there are 10 clients, and about 5 clients, they have only half labeled from, for example, from 0 to 4, and another clients, they maybe have 5 to 8. Yes, we have some code to random produce this kind of data distributions, and we use a degree. Like if the non-ID degree equal to 0, it means it can transfer to the ID, and the non-ID degree equal to 1, it means that, for example, there are 10 clients that each client only have one labels or one attribute. Yeah. Okay. So in this chapter, we introduce the blockchain to the decentralized factor learning, and we want to use blockchain to replace the aggregator, because we know that the blockchain can overcome the 1-point failure for the aggregator, and maybe the aggregator is not attractive. So in this work, we'll first introduce the procedures about the blockchain with factor learning, and also there are the one paper published in Science or Nature. I'm not very. They also have the quite a similar process. So for one attending client, have two part of job. The first one is like the local training, like the original client do, and the second one after he finished the training, he need to mining a block, and the published or the learned models will stored in this block, and other miners or other clients in this blockchain, they can also download or upload the learned models in this block to verify. So we use blockchain to replace the center server, and it's like the procedure for step 1 to step 8. Okay, and in this part, we know that the roles of the client, each client have two parts of job. So first one is like the training, and the second one is like the mining. So we use mining here. And if we consume, if we think that the computation result for each client is limited, so there have some like the computation allocation. In this work, we'll first do some convergence results for uh the mining is like we, because in blockchain, if we use the POW mechanism, every miner will try to mine it or do some work. You can think about to do some work to mine a block. The block is mere a package that is available to every client, and this package can be trustful. And in this block, the client can transfer the models or transmit the learned models to this block and stored in the block. So the so everything in this block cannot be changed. So it will be trustful. So it's kind of some related information about the blockchain. So it might is it clear? Uh, yes, as you mean that actually it don't have a central server because we said that maybe I didn't clear it. First, it in this framework it doesn't have a central server because we can see that each client will do the mining, and the first one he mine a block, he will act a role as a central server. So actually, it didn't have a central server, but a client who will change to a central server. Okay. So the second question is that yes, yes, proof of stake concepts will be used for this. Yeah, sure. The the proof of stake concepts can be used in this way, but because this is our previous work, we just use the POW, the traditional easy one to model the mining process. But we also can use a proof of state or proof of something like that. Yes, sure. So I continue the slides. Uh, because the client have some computation allocations, so the convergence analysis is quite different from the previous one, and we also do some like the impairment verification for the meanest and the fashionist data set. For example, the remark there also exists optimal communication round T. We call it the integrating round T. And in each integrated round, the client will do a mining once. And the second is we say the loss functions with number of the clients. We can find that it's also the currency, the loss function is convex, and a large number of participation clients will lead to a better learning performance. And in the second part, we want to conduct more or future in the decentralized federated learning based on blockchain, and we find a issue. We call it the lazy client issue in this framework. It's like this way. For example, because the mining, we define that the mining they can get a reward because in blockchain that we do the mining we can get some rewards, but the learning we do not have some reward. So some client will be lazy for the learning, but they will be active for the mining, and they can use his own computation result to do the mining, and just copy the the broadcast or the P2P learning models in the P2P transmissions. So we define that there's a lazy client problem, and this issue will degrade the learning performance because if a large number of clients they just copy other models and didn't do the local learning themselves, they will degrade the learning performance. uh, if we consider the privacy issue, actually, when we transmit the learning models, we can't preserve the privacy. Yes, but in this work, we actually we add noise. We add noise on the parameters. So because you can see that like the optional, there's different parameter, but I didn't explain here. So the way we consider now is just add noise to the uploading models. So this way we can to preserve the privacy. Okay. Okay. Maybe there are other ways to do, but we for our current works we only use DP, the DP to achieve to preserve the privacy. So to mitigate this copy or the lazy client behaviors, we use like the p-synchronous. The p-synchronous is quite familiar in the wireless communications, and it has a high cross correlation coefficient. So it likes when IV1 finish the training, it can add a p-synchronous to the models, and they have two effects. The first one is that uh, it will the it can mitigate the copy behaviors, and the second one it maybe in turn to degrade the learning performance because we can trace this random noise inject to the learning models. So there is a trade-off, and we will show so for example, the success detection probability is for the good, and the learning performance maybe degrade the learning performance is for the bad. Uh, so we do the result later, and we also do a convergence analysis for the PN sequence or without the PN sequence here, and we have two convergence bound without a PN sequence and with the PN sequence here, and they also they both have the result with the lazy client, and we define M as the number of the lazy clients. And we have the result. First is the testing loss for the meanest and the fashionist result. So they can show that convex with alpha and H. And the alpha H is like the way we define the lazy client. And the second one, we do a common result for the full data set. We can see that if we didn't consider appearance sequence or the like the defensive mechanism, we can show that with the lazy client, the 50%, 5%, 20% or 50, 40%, the learning performance will be degraded compared to the no lazy client. And if we consider the PN sequence with uh, a select not powers or the PN sequence powers, you can see that performance is increased. And although because we add random noise to the system models to the learning models. The performance is a little smaller than the original learning models. So he has a two part of it. It have two part of effects. Okay. So this is the end for the factor learning with blockchain, and we can continue to the last part. The first one is like it's still like the we contact to some wireless resource allocations in factor learning. The first one is also like the in factor learning with blockchain. As we mentioned before, that each client has two part of job. The first one is learning, and the second one is like mining. So he has to allocate the computing resource to this part. And in this work, we consider this in the system model. And we use like the client schedule, we define the whole system like the client scheduling problem in this way, because it's quite have a lot of the math operations and equations. So I didn't show the very details. And he has some in energy constraints like this one, and also the delay constraints. So to serve these optimizations, it did mean that the delay, we use Lyapunov optimization functions. We use the Lyapunov difference to transform the original problem to P1, P2, P3. We have the whole details in the paper. If you have any interest, you can check the paper. Okay, and we optimize the results and get optimize the equation serve the results. So we compare the dynamic optimization approach with other three client scheduling problems. First one is the client scheduling based on the channel state, and the EC means that the client scheduling based on the energy consumption, and I means all client scheduling. Okay. Yeah. The original problem is to minimize the delay, and we transform the delay to the utility by the Lyapunov optimization questions. Lyapunov optimization solution to P1 to P2 and P3. To tell the truth, that is not fully equivalent, but we because to tell the truth, it cannot be fully equivalent to the P3, but you know that we do some like approximations in this process. Okay. Uh, Actually, we gave some proof to show that the result or the solution for P3 is still available for P0, and we just compare the result for the other three. We can show that even though that the P0 to P3 are not quite quite equal, but we can show the solution for P3 is also can get best performance. So you can see that for this figure, we use MNIST and FashionMNIST dataset to compare the proposed result with other three algorithms, and we can see that we can achieve a lot, a smallest loss functions and the highest accuracy. And also see that for a given accuracy, for example, for the MNIST we need to achieve 90% accuracy, and for the fashion mid, we can achieve 80% 80% accuracy. The proposed algorithm will use a small list time, so we can achieve the minimal delay. Actually, you mentioned a very good questions. Yes. But we also know that in the optimization process or serving mode optimization process, usually we can do some like transform to a problem, or divide the whole problem into three or several sub problem and serve it. Yes. So the last work, so we just accept in this year in GSEC. We also want to achieve low latency in factor learning, and we compare the differential privacy in define a differential privacy for each user requirement, and we define some interference for the uplink and the downlink, and we want to minimize the whole transmission delay. For example, it have three parts here. For the tau D, it means the downlink delay, and the tau U means the uplink delay, and the tau L is mean the training delay. So we want to minimize the delay, and we define the optimization function in this way. It's like the max min problem. And we transform the max min problem to min max. We use reward to define the to transform the delay, and this is equal. We can say that this is equal, and also define the distributed model divergence. It means that in each in the client scheduling problem, the client scheduling process, each client or we cannot choose just a particular client. We have to choose almost every client to make sure that the distributed model divergence can be lost, can be the smallest. So we have the optimization problem, the P1, and we have some condition. And the C4 is for the model divergence conditions. And the first, the C4 is like the partition parameters, and we give the presence of the P4. C4 also have a performance analysis of performance represent about the theta I, and it means the distributed model divergence. It's linked with, so now in this equation, we link to the values to the learning in this equations. And the original problem is P1, and now we can max the reward to P2, and is equal. And we can see that this in this part is equal. And we use multi-agent, multi-armed bandit to solve the problem. It's like it's kind of like the reinforcement learning, but it's called multi-agent, multi-armed bandit. And he has action and reward, and action another reward. And we propose two solutions. The first one is modify the Hungarian algorithm in this figure. For example, it will decrease or prompt the minimal age of the graph. Each graph means the utility we marked here, and until the algorithm can't find the perfect matching. It's like the matching we have 2 channel and 3 client. We need to allocate each channel to 1 client. So in the first method, we have 8 edges. For example, E1, 1 and E2, 1, and we have 6. And we just prompt the minimal age, the minimal values of age. For example, the first we uh, uh, we prime the E12 because it has the smallest value. And in this one, we can allocate two channels to two clients with the red color. And the second one, we also provide a grid matching. And the grid matching is quite similar, quite simple with a greedy search. And he has a lot of complexity, but not a very good performance with the first one. So we also gave some performance, or it's kind of a convergence analysis for the multi-agent, multi-armed backend, and we gave a performance with log-t. The t means the iteration numbers. And last, we show the result. Okay, so first one we compare with other four like the client scheduling problem, scheduling algorithm, and we can see the OM is the first one. The first one has the best performance, the blue one, and the gradient have another uh, another the second performance. Okay, so I almost finished the talk today, and we'll talk about our future works. We also will focus on the resource limited factor learning. For example, we can use quantization or model compressions in the limited communication environment. And also can use speed learning or dynamic neural networks in the limited computing environment. And also can compare with the meta learning with factor learning to do the personalized factor learning. And we can consider non-ID distributions or the model diversities. Last, we are currently write a magazine paper about the vertical factor learning, because the vertical factor learning is more common in the business work now. So it maybe have a greater a future for the with compared to the horizon factor learning. So that's the end. Thanks everyone for your time. And if you have any questions, you can ask.